Salt hydrolysis. We move ahead to the formulas, we need to calculate about salt hydrolysis. Let me explain to you how many types of salt can we have. We can have a salt of a strong acid, a strong base. For example, if you take strong acid HCl and a strong base NaOH, we get how you will form the salts. Just identify the ions H plus Cl minus, Na plus OH minus. So this plus will go with this minus, this minus will go with this plus. What you will get? NaCl and water. So this is your salt. Salt of a, this is a strong acid and this is a strong base. So this is salt of a strong acid is plus a strong base. Similarly, if we take a weak acid, organic acids, all organic acids are weaker acids than mineral acid. Mineral acid, which are the mineral acids? Mineral acids are HCl, H2SO4, HNO3, HClO4, right? These are mineral acids. And organic acids are all carbon containing carboxylic acids, phenols, alcohols, these are weak acids. Whereas mineral acids, and out of them, six mineral acids are strong acids. Which one are those? HCl, HBr, HI, 3 hydrogen halide acids, yeah, or you can call them hydrohalic acids. HCl, HBr, HI, 3 of them are strong acids. Then you have HNO3, fourth one, H2SO4, fifth one, and HClO4. These six, HCl, HBr, HI, HNO3, H2SO4 and HClO4, these are strong acids. Other than that, all are weak acids. HCN is a weak acid, H2CO3 carbonic acid is a weak acid, carboxylic acids are weak acids, phenols are weak acids. So these are weak acids. And if you look for bases, NaOH, KOH, calcium hydroxide, these are stronger acids, whereas hydroxides of zinc, aluminum are weak acids. Amines, ammonia, these are bases, weak bases. Ammonia, amines, hydroxides of zinc, aluminum are weak bases. All right. So let's see. If I take carboxylic acid, a weak acid, and do a reaction with a strong base, this is a weak acid and this is a strong base. What do you get? Acetic acetate ion H plus, Na plus, OH minus. So what will happen? OH minus will go to H plus and form water, and acetate with sodium will form sodium acetate. So what kind of a salt this is? This will be called as a salt of weak acid with a strong base. Similarly, we can have salt of weak acid, weak base. For example, if I take weak acid, acetic acid, and we take a weak base, ammonium hydroxide, and you form a salt out of this, you have NH4 plus OH minus. So you get ammonium acetate, CH3CO, NH4, and along with that you will get water. So this is a weak acid, this is a weak base. So the salt form is salt of weak acid along with weak base. All right. So these are few categories of salts we can produce. All right. We have over here few formulas we need to calculate regarding hydrolysis of salt. So what are the things we are going to calculate? Will be calculating degree of hydrolysis. We will be calculating hydrolysis constant KH and pH of a salt solution. So let us go through them. So initially, if we have a salt of a strong acid, a strong base, it does not show hydrolysis, because ions before salt hydrolysis will be the same ions after reacting with water. So no net hydrolysis occurs when we have a salt of a strong acid, a strong base. All right. So no formula as I mentioned over here. Next, we are moving ahead with the salt of weak acid, strong base. Firstly, I'll give you a trick to figure out what type of a solution it will be. Just identify the stronger component. If a strong component is acid, final solution of the salt will be acidic. If a stronger component is base, then final solution of the salt will be basic. For example, if I take sodium acetate, it is formed from NaOH and acetic acid. Acetic acid is a weaker acid and NaOH is a stronger base. So overall, the solution of sodium acetate is going to be basic. Similarly, if I take a salt of weak acid with a strong base, which I took initially, now I'll take the other way around. I'll take a strong acid and weak base, ammonium chloride. Ammonium chloride is a salt of ammonium hydroxide and HCl. So the final solution of ammonium chloride will be acidic. All right. So these are the hints you need to remember. And what will be the solution of a strong acid and a strong base? That will always be neutral. pH will always be equals to 7. All right. Next, you have few formulas, and I'll tell you the trick. It's very easy. If one of the component is weak, then you use these formulas. You will easily be able to remember this. So Kw by K into C when acid is weak, and hydrolysis constant will be equals to Kw by Kb into C when base is weak. Alright. When both are weak, then you get a formula H equals to root of Kw. So there won't be a relation with K or Kb when both are weak. Alright. Next, if you have Kh equals to Kw by K when acid is weak, Kh is equals to Kw by Kb when base is weak. When both are weak, then you will have both K and Kb at the denominator place, right? Next, you have formula for pH. pH equals to half of pKw plus pKa plus log C when acid is weak. Just remember this, pK is for acid and pKb is for base. Which kind of a base? Weak base, and this will be for weak acid. Alright. Now, how you are going to remember this? Just remember the formula is of sodium acetate. So pH is going to be definitely greater than 7. So half of pKw is 7. So something has to be added. So what you are adding? pKa plus log C, right? So the pH is going to be greater than 7. Now in this salt you have ammonium chloride and you have a strong acid, that means pH is going to be less than 7. So something has to be subtracted from 7. So the formula goes like this: half of pKw is 7, so 7 minus pKb plus log C, right? If you want, you can put a bracket out here, right? So this will be plus here pKa plus log C and here pKb plus log C. Whichever is weaker, use that dissociation constant. Here plus because the pH is higher than 7. Here outside will be minus because pH is less than 7. And in the last case where we are taking weak acid and weak base, you have a easy formula where you have to just memorize half of pKw plus pKa minus pKb. From that, relative strength, whichever is slightly more, one will be less weak, another will be more weak. So whichever is less weaker will dominate the other one. We cannot predict whether pH will be greater than 7 or less than 7. Both the things are possible in this case. So here we complete salt hydrolysis. So today's topic is concepts of acids and base. So we have three theories which are very popular. The first theory and the oldest theory is Arrhenius acids and bases. And the second theory is Bronsted acid and base theory. And the third and the latest theory is Lewis acid and base theory. Alright, so let us understand what does it explain. So Arrhenius acid and base theory tells us about Arrhenius theory tells us about that H plus donor is acid and OH minus donor is base. Alright, I hope you know the examples. Example could be HCl, H2SO4 and so many other acids very commonly known to you, and bases are NaOH, KOH, calcium hydroxide, magnesium hydroxide. These are Arrhenius bases. All right. So next is Bronsted and Lowry acid and base concept. Bronsted and Lowry acid base concept. So Bronsted and Lowry concept, what does it say? It says H plus donor is acid, H plus donor acid, and H plus acceptor is base. H plus acceptor is base. All right. So what do you understand from there? It doesn't talk about OH minus because there are certain bases which do not give OH minus, but overall the solution is basic. So it deals with those bases such as ammonia, amines, because they are basic but they do not have OH minus, so they do not produce OH minus, but still they are bases. All right. For example, the examples are same here, HCl, H2SO4 and all those. But here examples are not the ones which had OH minus. You will have ammonia, amines. These are certain bases which are specifically Bronsted acid, Bronsted bases, but not the Arrhenius bases. All right. And there is a concept, conjugate acid base theory. For example, if you have acetic acid, it gives out H plus, it forms acetate, right? And if you add H plus, it forms acetic acid back. So acetic acid is known as conjugate acid, right? And this is known as conjugate base. So conjugate acid base theory is Bronsted acid base theory. There is a difference of one H plus. If you remove one H plus, you form conjugate base, and if you add H plus to the conjugate base, you get conjugate acid. Let me tell you, there are few examples we have which can behave as acid as well as base. For example, water. So what do you see in water is that water has the tendency of both. It can give H plus, and form OH minus, and it can add up one H plus and it will form H3O plus. So water can act as acid by giving H plus, and it can behave as a base by accepting H plus. So water can behave as acid as well as a base. So we call water as amphoteric. Amphoteric. There is a term called amphoteric species which can act as acid as well as base. So water can behave as both acid as well as a base. So water, if I consider this pair H2O and OH minus, so water is conjugate acid and this will be conjugate base. If I consider H2O and H3O plus, H3O plus, so what is there? H3O plus will be conjugate acid and this will be conjugate base. Alright. So considering the pair, then we can understand which is acid and which is base. The one which gives H plus will be the conjugate acid. The one which adds up H plus will be the conjugate base. So there are amphoteric species as well which can behave as both. HSO4 minus, H2O, ammonia, these are species which can behave as both. Amphoteric species we call them. Bronsted and Lowry concept we have explained. Arrhenius concept we have explained. We will be talking about other concepts later.